Okay, good morning. Welcome to the last complete week. We're almost there. So please don't give up. Please keep going. Like I've said, the last couple of weeks of this course are very important for the final exam. So on Friday we ended talking about Green's theorem, which is a way to calculate a vector line integral using a double integral instead, which is very helpful when the fields we are dealing with are not conservative. Recall that if we are dealing with a conservative field and we're asked to do a vector line integral, we should really consider the fundamental theorem of calculus, which says that that vector line integral is equal to the difference in the potential function's value at the start and end point of the curve of interest. But if the vector field we're not dealing with is conservative, we can't use the fundamental theorem of calculus. So to avoid nasty vector line integrals, we can use Green's theorem instead, which applies for closed curves in a plane. So for instance, in the xy plane, if you have a curve, for instance, a circle, a closed curve, and you're asked to find the vector line integral around that closed curve, and it's not a conservative field. If it was a conservative field, it would be easy, it would be 0. But if it's not conservative and you're asked to find the vector line integral around a closed curve in a plane, for instance, the xy plane, you should really think about Green's theorem, which allows you to convert that vector line integral to a double integral over the region of that closed curve, which it may not be, but often is easier to solve. So that's what we finished with on Friday. Okay, so what we want to end off with in the course, and then I mentioned that I lied to you, we do need one other type of integral in order to do the last couple of theorems in this course. We need a surface integral, which is not a big deal because it's a double integral. But all the double integrals we've done so far were in a plane, right? In the xy plane, our region of integration R was in the xy plane or the yz plane or in a plane. What happens if we have some sort of three-dimensional surface in space? Can we calculate a double integral over that surface? And the answer is yes, and that's what a surface integral is. Why do we need surface integrals? Because they're very handy for calculating what's called flux. And you might have come across the word flux somewhere before. You've probably heard of magnetic flux or flux density. Okay, we use flux in a number of different applications in engineering. Transport flux. We often talk about transport flux, where something is being transported. For instance, heat. Heat is flowing through some material, so we talk about heat flux. We talk about electrical flux due to an electric field. We talk about magnetic flux due to a magnetic field. Okay, so we use flux in a lot of different areas in engineering. What is flux itself? Flux is just the flow of something, the rate of flow of something through some area. Okay, flux is just the rate of flow of something per unit area. So if we're talking about heat flux, for instance, what would be the units? Well, we use, for instance, joules, right, for heat. So it would be joules per second. That's the rate of flow of joules. Joules per second, for instance, per meter squared. Okay, it's a rate per unit area. The rate of flow of something. So for heat flux, it would be that, right? A mass flux, if you've got mass flowing or moving, it would be kilograms per second meter squared. So we often want to calculate flux. Flux that's crossing some surface, okay? And that's what we use a surface integral for. So flux as a surface integral. So if we have some vector field, for instance, an electric field is a vector field. We can talk about, maybe that's not a good one to use. What would be a better one? Well, let's say some liquid that's flowing, some fluid that is flowing, okay? And we want to calculate the flux of this fluid that crosses some surface, okay? We want to calculate the flux of that fluid. We can use a surface integral, which is a double integral, okay? And double integrals in the past, the region of integration was capital R, right? It was some region in the XY plane, typically. Here it's going to be a surface S, okay? The region R, when we did double integrals before, the region R was also a surface. It was just in a plane. It was part of a plane. Here it doesn't have to be part of a plane. It can be some wavy surface in three-dimensional space that we're going to calculate the surface integral over, okay? So it's the region of integration again, okay? So just like double integrals, there's two things going on. There's the region of integration, this time S, and there is what you're integrating, which is going to be some vector field F, okay? And it's a surface integral, so it's dot dA, where A is also a vector. So what we're integrating is the dot product of two vectors, our vector field and this thing called dA. And dA we can rewrite as n hat, which is a normal unit vector, dA. Okay, so n hat dA is a vector. N hat gives the direction of this vector. dA gives its magnitude. Okay, so this is this vector dA. Okay, so again, what the surface integral, if F is a vector field, it's going to calculate the flow rate of something per unit area. If it's an electric field, it's the flow of this electric field through some unit area, okay? So you will see somewhere, if you go into electrical, you'll see somewhere this. Okay, that would give us the flux of this electric field. Again, over some closed surface. When we put a circle on this, it means a closed surface S. Maybe a sphere, maybe a box, a cube, right? As opposed to an open surface, which is just a surface. So we see that, for instance, if we're dealing with electric fields. If we're dealing with magnetic fields, you'll see something like this. We typically use B for the magnetic field of a magnet or an electromagnet or something, right? Okay, so if this calculates flux, what is the flux a function of? Well, we can see it's a function of three things, okay? If we go back to this important equation. How do we know how much flux we have, or what determines how much flux we have passing through this area? Well, it's going to depend on the strength of this field. Obviously, the larger our field, or the stronger our field, the more flux it will generate. Okay, that makes sense? It's also going to be determined by our surface S, right? If I've got a bigger surface, well, this field, there will be more of this field passing through that surface. I'll have more flux. So the size of S here will matter as well. This is also a dot product. So remember what a dot product is. It's the magnitude of this times the magnitude of this times the cos of the angle between them. And if that angle is equal to 0, what does this equal? We did this in the first week. Dot product. If the angle between these two is 90 degrees, is that what I said? Did I say 0? Okay. If the cos, when will I get the maximum amount? What will for what value of theta, which is the angle between these two vectors, will I get the maximum dot product? 0, right? Because cos of 0 is 1. If the angle deviates away from 0, the cos becomes less than 1. So this gets smaller. When is this equal to 0? When theta is equal to 90 degrees, right? So the relative orientation of these two vectors, because this is a dot product, will also impact how much flux we have, okay? So there's a good diagram. Let's take a quick look at it in the lecture notes. Albums. This one here. Okay, if we look at that, so this circle or this ellipse corresponds to our surface S, okay, and the lines correspond to our vector field F. You can think of it as an electric field, a magnetic field, or you can think of this as fluid flow, whatever you want, okay? Obviously, the stronger my field is, so this would be a stronger field because they show more lines, right? The more flux I'm going to have if F, or let's say E, is bigger, okay? Obviously, I'm going to get more flux for the same surface, S. If my surface is smaller, I'm going to get less flux. In this case, we've got the same strength of electric field. The spacing between these field lines is the same here and here, indicating my vector field is the same here, but now my surface S is smaller. Obviously, I have less flux. Okay? If this is fluid flow and this is the size of my pipe, obviously I've got more flux in this pipe than I do in this pipe, obviously. Okay? And the relative orientation. So again, these lines are my vector field E, if you want to think of it. Okay? I'm going to have more flux through this pipe, through this surface S here, if I orient it like this with respect to the field than if I orient it like this. Okay? So this here, the angle between this and this would be equal to 0. Okay? Here it's not going to be equal to 0. Why would it be 0 here? Well, because this is a dA, and remember this dA is an n hat times dA. This dA is going to be like the surface area of this. This n hat is going to be the orientation of this in free space. And it's going to be, n hat means it's a normal vector, a unit normal vector. It's going to actually be, it's going to look like that for that surface. That's my n hat. It's normal to my surface S. Right, that's my surface S. N hat's going to be normal to it. For this surface S over here, what's n hat going to look like? It's going to look like this. Okay, now you can obviously see that the angle between n hat and my field here is 0, which gives me, right, if I take the dot product of two vectors where the angle between them is 0, I get the maximum amount of that dot product. In this case, the angle between my vector field and n hat is not 0. So the cos of that is going to go down, so I get less flux through this case than this case. Okay, so that's what flux depends on. The size of the field, the size of the surface, and the relative angle between the field and the surface, where the angle of the surface is determined by this n hat, which is always a unit vector that's perpendicular to the surface. Okay, so let's just draw a generic surface in 3D space. Maybe it looks like this. Maybe that's our surface S that we want to calculate the flux through. Okay, well, again, it's not a plane, it's not flat, like in a double integral where our region R of integration is flat, it's part of a plane. It's not part of a plane, but if we make it really, really, really small, we take a little patch of that, okay? It's got area dA, which is really, really small. And we draw a unit vector that's normal to that, call it n hat, okay? We could calculate the flux through that little patch, which is more or less flat. And it's so small that the vector field F is constant everywhere inside that little patch, right? Because remember, our vector field F could look something like this. Right? Maybe it looks like that there, maybe it looks down here, it looks like this, right? The vector field F doesn't have to be uniform throughout space. It could vary. It could be a function of x, y, and z. right? It'll have a particular value right at that point too. Maybe it looks like that there. Maybe everywhere in that patch, because the patch is so small, F is constant everywhere within it. So now we could calculate the amount of flux there, just F dot n hat dA. And that would be the amount of flux going through that little patch, right? We do that dot product. N hat, there's angle between n hat and F, that's equal to theta. And we can calculate that dot product, we got the flux. But now we want to do it over the whole surface. Well, it's a surface, so we're going to use a double integral, right, over the surface S. We're going to sum up the flux through all the little patches dA over the whole surface, and that gives us the total flux through that surface S. Okay, in order to do this, though, we got to look at some details, okay, because it's not just a normal double integral like we did before. First of all, we've got to think about the direction of n hat. Here, let me draw a little bit bigger patch here. And I drew n hat like that. Okay, n hat has to be normal to the surface. Is that the only n hat I can draw? No, I could draw one like this, right? Underneath, pointing down. As long as it's normal to the surface. I would have two choices of n hat. Which one am I going to choose? Well, for an open surface like this, it's up to you. For an open surface, you can choose either n hat. Okay? But when you make a choice of n hat, you have now oriented the surface. And oriented to the surface means you've decided which direction is positive. Because remember, we've got an electric field. I'm an electric engineer, so I always think of electric fields. We've got some sort of vector field. Maybe it looks like this. Okay? And if this is my surface, like that, well, when I calculate the total flux, that flux is either going to be positive or negative. Because there's a direction of flow involved, right? Flow has a direction. It's got a magnitude and it's got a direction. It's the amount of material flowing in a particular direction. And I've got two directions that can go through that surface, okay? Obviously, the flux is going this way. So if I choose, now for this surface, it's an open surface, right? It's not closed. A closed surface would be a sphere or a cube, right? This is a circle in space somewhere, okay? I have two choices of n hat. I can say n hat looks like this, or I can say n hat looks like that, okay? I can choose either one because it's an open surface. If I choose n hat to be, I'm going to make this one blue. If I choose n hat like that to calculate my surface integral, which is calculating the flux, do you think I should get a positive flux or a negative flux? Somebody said some positive. If I choose this n hat, for that vector field F, I should get a positive flux, right? And if I choose this n hat, for that same vector field F, should I get a positive flux or a negative flux? Negative, absolutely. See, it's not so hard. It's not so hard. Okay? Now, obviously, if my F vector field was in the opposite direction, okay, so if my vector field, same surface, let's say my vector field looked like this now. That's my vector field F. If I choose that for n hat, and I calculate my surface integral, am I going to get a positive result or a negative result? Negative, right? If I choose this one for n hat, am I getting a positive or a negative result? Positive. Yep. Okay, so when we choose n hat, we orient the surface, which basically means we say, you can think of it as, well, the direction of n hat becomes positive. So if I choose this blue n hat, for this case that F looks like that, that means this is the positive direction through the surface S. If my F is in the positive direction, I'll get a positive flux. But if I choose this n hat, meaning going through my surface in this direction is considered positive, and my F actually goes in the opposite direction, well, that would be negative flux, okay? Okay, so that's all there is to that. You have a choice. For open surfaces, you got a choice. Actually, for closed surfaces, you do too. But conventionally, for a closed surface, by convention, we choose out. For positive. Which means we always choose the n hat that goes out, okay? So for instance, if we're dealing with a sphere, that's our surface of integration. Well, again, I have two choices, right? I could choose n hat like this, or I could choose n hat to go in towards the center of the sphere. I again have two choices, and actually you could choose either one, but somewhere in the past people decided we're going to choose outward for a closed surface as always positive. So that's what we're going to do too, okay? So outward is always, we always choose n hat to be pointing out of our closed surface, which means out of the surface is considered positive flux, into the surface is considered negative flux. Okay, so that's the first thing we got to talk about. And again, in this case up here, we would write our flux integral like this, S F dot n hat dA, okay? Down here for a closed surface, we just put a circle on the integral sign. So that means S is a closed surface. Sphere, a cube, some sort of closed surface, okay? Okay, so let's do a quick example with a closed surface. We haven't even figured out how to do surface integrals yet, that'll come. But let's say we've got a vector field F like this, X, Y, Z. And our surface S is the sphere with radius A centered at the origin. Okay, so that's a closed surface. How do we get n hat? Because we need it to calculate the surface integral. Well, first of all, we're going to choose n hat to be out of the sphere, right? N hat is a unit vector, means it has a magnitude of 1. So that's easy. Need a direction. Well, if our sphere is centered at the origin, we know the coordinates at the center of that sphere, right? It would be 0, 0, 0. We also know that if we drew a vector from the origin to some point on the surface of the sphere, and it extended it out of the sphere, that would be the direction of our unit vector, right? You've got a sphere, and you've got a vector starting at the origin, going in any direction, it's going to pierce that surface of that sphere. At that point on the surface of the sphere, we've got an n hat. We've got the direction of n hat. It's that vector. right? So this is O, and we've got a point on the sphere here, P, which is x, y, z. Well, then we can form a vector O to P, right? And we would know that that vector is perpendicular to the surface of the sphere, correct? And that's the key characteristic for n hat. It's got to be perpendicular to the surface, the closed surface we're dealing with here. We know OP would be perpendicular to the surface of the sphere. So it's in the right direction. If we turn it into a unit vector, we've got our n hat. Okay? Okay, well, what would the vector OP be? If the coordinates of P are x, y, z, what's vector OP? We did this way back in the first week of lectures. X, y, z, right? It's the coordinates of the end point of the vector minus the coordinates of the starting point, which are 0, 0, 0. So it's x, y, z. Okay, so that's our vector. Now we just got to turn that into a unit vector. So our unit vector n hat is going to be OP divided by its magnitude. And what is that magnitude? What is that magnitude equal to? What is this? The square root of x squared plus y squared plus z squared is equal to what? What's the equation of a sphere? Yeah. R. And R is equal to? It's the radius, in this case A, right? Because remember, what's the equation of a sphere? X squared plus y squared plus z squared is equal to r squared, and we were told r is equal to a, so it's that. So obviously the square root of x squared plus y squared plus z squared is equal to just to a, right? So our unit vector is 1 over a x, y, z. That's our n hat. Okay, well, we know that in the surface integral, we're going to, it's equal to f dot n hat dA over this closed surface, which is a sphere. We know f is equal to x, y, z. We were told that. Oh, better write the integral sign again. We were told f is equal to x, y, z. And we found that n hat is going to be equal to 1 over a x, y, z. Okay, so and then we got dA out here. So what is this equal to? 1 over a x squared plus y squared plus z squared dA. And x squared plus y squared plus z squared on the surface of the sphere. Because remember, we're doing a surface integral, which means everything that inside here is on the surface of this sphere. It's on the surface. So on the surface, what is x squared plus y squared plus z squared equal to? On the surface of the sphere, what is x squared plus y squared plus z squared equal to? It's equal to a squared, right? From the equation of the sphere. On the sphere, this is equal to a squared. So we're going to end up with a dA. Okay? A is a constant, so it can come out of the integral. dA. Now, we don't know how to solve the surface integral yet, but remember, dA is a small patch of area on this sphere. It's the area of that small patch. And if we add up the areas of all the patches on the surface of the sphere, we get the total surface area of the sphere, right? This is just the surface area of the sphere. Which, if you Google it, is equal to 4 pi times the radius squared. 4 pi times the radius, which is a squared. So the result is 4 pi a cubed. That's the flux. Okay, so even though we don't know how to solve the surface integral yet, we could solve this one because it's pretty easy. Because the integral just turns out to be the total area of our sphere. Okay, and then we're good students, so we look at our answer and we just don't rush on to the next question. We look at it and go, does this make sense? Is this a positive number or a negative number? 4 pi a cubed. Positive or negative? Positive. We know it's got to be positive. Can the radius be negative? Not in this universe, right? So a is a positive number, so 4 pi a cubed is a positive number, which means our flux is positive. Does that make sense given the direction of n hat and given the direction of f? F is our vector field. What direction does f point? This is a radial field, so f is always pointing out from the origin, right? F looks like this. So the flux of F is going out of the sphere. And we chose n hat to be pointing out of the sphere, which means out is positive. Should we get a positive result? Yes, we should. So at least that part makes sense, okay? Okay. Okay, well this was easy because we didn't actually have to solve this integral. When we get to this point, we know conceptually that we're integrating across the surface S. We're just adding up all the areas of all the patches of this surface, which gives us the total area of the surface. Surface is simple, it's a sphere. We Google what's the surface area of a sphere. We find out it's 4 pi a squared, or 4 pi radius squared. But what happens if we don't know that? We've got to actually solve the surface integral, right? But unlike unlike our double integrals in the past, we solved them in 2 dimensions. For instance, our region of integration R was in the xy plane. Here, our surface is in 3 dimensions. So how do we solve a double integral in 3 dimensions? I don't know what number I'm on, but how do we solve a double integral in 3 dimensions? Well, in a double integral, how many variables of integration can you have in a double integral? How many variables of integration in a double integral? 2, right? You can only integrate 1 variable at a time. You got 2 integrals, you can only integrate 2 variables. But a 3-dimensional surface requires how many variables to define? 3. Okay? We can only integrate on over 2 of them. What do we do with the 3rd one? We hold it constant, right? If it's constant, it doesn't matter to us when we integrate the other 2, right? Just like when you did a double variable in xy, when you took the integration of x, what did you do with y? You held it as a constant, right? You treated it like a constant while you were integrating x, and when you were integrating y, you treated x like a constant. Okay, well now we got 3 variables. We're going to choose 2 of them over which to integrate, and the 3rd one we're going to keep constant all the time. That's basically what we do. So we've got 3 choices. We can define our surface with x, y, z. We can define our surface with r theta z, that was cylindrical. We can define our surface with rho phi theta, that was spherical coordinates. Okay, we've got 3 choices for a surface that we can use. Obviously, if you're dealing with a surface that's a plane, or part of a plane, x, y, z is probably the way to go. If you're dealing with a surface that has a cylindrical nature to it, r theta z is the way to go. If you're dealing with a surface that is spherical in nature, rho phi theta is the way to go. Okay? Now, obviously, there's all sorts of surfaces. We're only going to look at some of the basic ones. Okay? So we're going to look at... which one are we going to start with? We're going to start with spherical surfaces first, since that was our first example, right? And so no matter which one we use here, we got to remember our integral was f dot n hat dA. F we're usually given. N hat, we know how to get that now, right? It's got to be a unit vector that's normal to our surface. What is dA? Well, if we choose to use Cartesian coordinates, right? dA means what? dA is equal to what? It's going to be d something with maybe something in front of it. So if we're dealing with Cartesian coordinates, this could be just be dx, dy, for instance, if z is a constant. So that would be for the plane z is equal to 4. We could calculate the surface integral of that. We can do, it's just a regular double integral. So that's kind of boring. What about rho phi theta? dA is going to be equal to what? Well, we have to choose two variables of integration. So think of a sphere, the very simple example we started with. Of the three variables, rho, phi, and theta, for a sphere, on the surface of that sphere, is any one of those a constant? Rho, right? Everywhere on the surface of the sphere, rho is constant. So that would be a very natural candidate. So we would use d phi and d theta as our variables of integration because rho is a constant for our surface integral. But is there something in front of that? Yes, there is. We got to figure that out. If we're dealing with a cylinder, whose center axis is the z-axis, then is any of these constant everywhere on the surface of that cylinder? We've got a cylinder, and the center of that cylinder is the z-axis. On the surface of that cylinder, on the walls of the cylinders, not the ends, on the walls. The ends aren't part of the cylinder, it's just the wall of the cylinder. Is anything constant? R, exactly. So our dA is going to be equal to something d theta dz. Because R is constant everywhere on that surface of that cylinder, right? So we got to figure out what these dAs are, and then we got everything we need, pretty much, okay? Okay, so we're going to look at 4 different types of surfaces, and that's all we need to know for this course, okay? They cover a lot of the different cases. So case 1, we got a spherical surface. Let's start there because we've already done a simple example of a spherical surface. Okay, well, there's a whole bunch of geometry you can do. Let's just bring up a picture of the end result. So here's a sphere. Okay, and on the surface of the sphere, we're looking for a dA here. They call it delta A. We can just call it dA. If it gets really, really small, delta A turns into dA. Okay, well, we're going to use spherical coordinates. So you know you've got the radius. The distance of this patch from the center is the radius. The angle between the z-axis and the line that goes from the center of the sphere to this little patch is phi, and theta is this angle from polar coordinates, okay? If we zoom in on that and pick okay, if we zoom in on that, we can use geometry, basically trig, to figure out what are the dimensions of this little patch, dA. Okay, if we make it small enough, it basically becomes a little square. Okay, and so it's just this dimension times this dimension. So you can figure out what the lengths of these sides are with all these angles and whatnot. Don't worry about, you're not going to have to derive it on the exam. We give this expression to you, but you should know where it comes from. So it's obviously going to be just this times this. Okay? And instead of deltas, write d. So our dA for a spherical surface is going to be a squared sine phi d phi d theta. So that's what you get when you multiply a sine phi, again, instead of delta, think d. So a sine phi d theta times a d phi. We get a squared sine phi d theta. So that becomes our dA in our surface integral if our surface is spherical. Okay, what is n hat? We already know that from that example we did. For a sphere of radius a, what would the n hat be? We found that that was 1 over a x, y, z. Okay, and if you look at the formula sheet for the final exam, that's been on Canvas for at least a week now, you'll find these there. Okay, so we have n hat and we have dA for our surface integral. The other thing we have to do is very often we're given our vector field f, which is also in the inside the integral. We're usually given that in terms of x, y, z. Okay? Again, we're only interested in what the vector field is doing on the surface of that we're integrating over. Okay? So we have to change x, y, z to rho phi theta if we're going to use rho phi theta, right? So we have to use these. X is equal to a sine phi, cos theta. Y is equal to a sine phi sine theta. Z is equal to a cos phi. Again, a is the radius of our sphere. So we're going to have to express our vector field f in terms, not in terms of x, y, z, but in terms of the variables of integration we're going to have, which are rho, phi, and theta. So you're going to have to do that too. Okay, so our surface integral becomes f dot n hat dA. If f is equal to mnp, right, expressions of x, y, and z, m, n, and p. Our surface integral becomes that. F dot n hat dA. Right, this is f. This is n hat. This is the dA that we just wrote. Okay, and we have to replace all the x, y's, and z's with these expressions here. Okay, now we're going to integrate over a spherical surface. Now the surface S is not necessarily an entire sphere. If it is, it could be, and if it is, what would the limits for phi and theta be? Because the one thing we're lacking here is the limits on our integrals. We're integrating phi and theta over a whole sphere. What would be the limits for phi? Phi is the angle from the z-axis down. So what are the limits for phi? If we're over a whole sphere centered at the origin? 0 to pi, theta would be 0 to 2 pi. What if our surface was just the top half of the sphere? That could be. Okay, it doesn't have to be an entire sphere. What would change in the limits? If it was just the top half of the sphere. Phi would go from what to what? 0 to pi over 2. Theta would go now from 0 to still 2 pi, right? What if I took the top half of the sphere and I threw away half of it? What would change for phi? Anything? No, still 0 to pi by 2. What about theta? 0 to pi or minus pi by 2 to pi by 2, right? Okay, so the surface doesn't have to be a whole sphere. It can be part of a sphere. And the limits will define that, okay? Okay, so I don't think I'm going to do the example. It's so simple, no big deal. Let's move on to case number 2. Case 2 is a plane surface. For instance, Z is equal to A, right? A is a constant. So that would be a plane at the value of Z So this plane would be parallel to the xy plane, right? So maybe z has this value, so we've got this plane here like this. And of course, it goes on to infinity in every direction. I'm only drawing part of it, right? This would be the plane z is equal to a. Okay, again, well, we take a small patch of that. And this would be our dA. And obviously, what is dA? You take a small square patch of that. dx dy, right? Z is a constant. So the two variables we're integrating on this surface integral are x and y, because z is constant everywhere on this surface. If I had a surface x is equal to a, what would my two variables of integration become? Y and z, because everywhere on this surface x is equal to a, x is constant, it's equal to a, so I'm going to integrate over y and z instead. Okay, so just because I show you this one doesn't mean it's the only plane that you can do. Okay, so dA is that. What about n hat? We need n hat. Well, we got two choices. We can choose n hat like this, or we can choose n hat like that. Is this a closed surface? No, it isn't, so there's no convention. You can choose whatever you want, right? I could choose n hat to be equal to what? K hat, because k hat is the unit vector that points in the positive z direction. Or I could choose n hat to be negative k hat. My choice. If I choose positive k hat, that means positive flux would be going up through that surface. Negative flux would be going down through that surface. If I choose n hat equal to minus k hat, that means positive flow would be down through the surface. Negative flow would be up through the surface. My choice, okay? So obviously now, our surface line, our surface integral, S, f dot n hat dA is going to be equal to f, which is, again, given something like that, dot, sorry, I'm going to go down here, n hat, which would be, let's say I'm going to choose k hat. That would be that. That would be k hat, right? Positive k hat up. And dA is dx dy. Okay, so this surface integral is going to become, when I do this dot product, I'm obviously going to get P dx dy. Right, where P is the z component of my vector field F. And P itself could be a function of x, y, z. Right? This P is this guy here. But remember, I'm only interested in my vector field F on the surface. And on the surface, what is z equal to? A, right? So this becomes, so wherever I've got a z in this expression, it becomes an a. Oh, that's not a vector. Okay? So this p becomes I replace all the z's with a in that p. Okay, and the limits of this integral are going to be dictated by, okay, how much of this plane z is equal to a am I finding the flux through, right? X is going to have a limit, from there to there. Y is going to have a limit from here to here, okay? And I do my integral. No big deal. So if you're given and S is equal to Z equal to 0, where X goes between 0 and 2, and Y goes between 0 and 3. Okay, my surface integral is pretty simple and straightforward. Right. So what is, I need an n hat. So let's say n hat, I'm going to choose it to be positive k hat, which is equal to 0, 0, 1. So I take the dot product of my vector field f with 0, 0, 1. I'm going to end up with 3. So I get 3 dx dy, where x goes from 0 to 2, y goes from 0 to 3. Pretty simple integral. You get 18. Okay, we'll stop there and keep going on Wednesday. Sorry to keep you a couple of minutes late.